let's get started then. Welcome everybody to another session of Spacetime after quantum gravity and the local Geneva group here, which again will be live broadcast, Skyped to Chicago, as you all know right now how this works. It is my very great pleasure to welcome today's speaker, Francesca Vidotto, from the Roundabout University in Nijmegen in the Netherlands, where she's working on a project on quantum gravity, and her title is, oh sorry, already skipped to the next one, to the next slide. Anyway, without further ado then, Francesca Vidotto on how classical space-time emerges in loop quantum gravity, please.
Yeah. Thank you very much. Thank you for having me here today. And yes, so I'm really glad to be part of this project about space and time after loop quantum gravity. That is a concrete realization of a possible theory of quantum gravity. So, yeah. So of course, having such a new theory for spaces and time makes more urgent to address the standing questions in philosophy of space and philosophy of time. So questions are such as what is space, what is time, and we have answers from the ancient time to today, different answers from philosophers, and what I would like to do today is to try to shape what are the answers that a concrete realization of a theory of quantum space-time give us now. Of course, then the question is if there is a regime, a quantum regime, that is the one in which h bar is different from 0, is a regime in which the Newton constant is non-zero, and it's a relativistic regime in which c, the speed of light, is less than infinity. So the question is whether in such a regime, a full relativistic quantum regime, is there a sense in which we can talk about space-time or not? And then there is this question that seems to have a lot of attention in these days, in which sense there is an emergence, if any, of space-time. And okay, this is my main questions, and then I may try to address very briefly, more details will be given tomorrow in a talk here in Geneva, about in which sense some people are asking whether classical space-time may emerge in the same way in which from a statistical theory you have thermodynamics. So the idea is that you have to take a thermodynamical limit to get classical space-time. And so I will argue about this later in my talk. Okay, so these are the questions that I want to address. And well, I take it from very far, from the general picture of given by contemporary physics about what exists in a physical theory. Well, I don't want to make all the history. This is something you know better than me. My starting point now for this talk is here. It's the ontological picture that we had from the 20th century, in which after Faraday and Maxwell, we know that there are not just bodies or particles, but there are two different entities that are particles and fields. And in the relativistic quantum theory, it's quantum field theory, those objects are part of the same entity that are the quantum fields. And these quantum fields interact with some space-time that for the moment is just a fixed background where already space and time has been merged after Einstein's special relativity into a unique object. So we start from there. We have quantum fields, and we have some fixed stage on which these fields live. That is our spacetime. Okay. So I represent here this fixed stage background, this gray square here, on which the fields live. And then I consider the quantum theory of those fields. And in the quantum theory of those fields, I have a lot of quanta living there. As I said, fields and particles are two aspects of the same object, the quantum fields. So I can represent them in this way. And so if you think about electromagnetism, those are just photons. Okay, so how do I characterize such a theory? Keep in mind what you may know about quantum electrodynamics, so the quantum theory of electromagnetism. What are the mathematical objects that characterize, with which we characterize this theory? Well, we need, as usual, in quantum mechanics, remember what you know from your course of Foundations of Quantum Mechanics, we need a Hilbert space, we need a set of observables, an algebra of observables, and we need the dynamics. So the dynamics, okay, so if we consider the case again, the case of photons, my states living in the Hilbert space are living in the so-called Fock space, in which I can have a creation and annihilation of quanta. So my observables, my operators are those A that are creation and annihilation of operators, acting on the states that are those of the Fock space. Okay. And then, okay, Hilbert space observables, this characterize the kinematical part of the theory, but then I need the dynamics. The dynamics is given by this W. And careful, when I do quantum field theory, the dynamics is given in terms of probability amplitudes, transition amplitudes. So the dynamics are a set of rules, the Feynman rules. So I can write, after Feynman, I can write these rules in a very appealing way using graphs. I can use those rules to write down an integral, and this integral gives me back the probability to go from a certain state to another state. For instance, I have a state with a couple of photons. I want to know the probability to go into a state with 5 photons, for instance. This is what defines the dynamics. Then, yeah, okay. This is just my Feynman diagrams, and please forget about this expression in which there is a typo. Then, yeah. Then, so I have a theory that is discrete. It's discrete because the observables that I can write down, they have a spectrum, so they have a set of possible value, realizing them, and this set of values is discrete. It's just some, not a continuous of possible values, but I can get only discrete numbers. Or for the photons, for the creation and annihilation operators, so for instance, I can define a number operator. So for particles, obvious, I can have 1 particle, 2 particles, and so on. So in the quantum theory is characterized by the presence of a discreteness. It's also characterized by the presence of fuzziness, because the quantum operators, my observables, the physical quantity that I can describe, they don't commute. And therefore there is, because after the Heisenberg relation, the Heisenberg uncertainty principle, I know that I cannot sharply have a sharp value of one quantity having the other sharp as well. Finally, this is what I was stressing before, the theory is probabilistic. The dynamics is in terms of, is defined in terms of probability to go from one state to the other. Okay, that's the quantum theory. When I go to the classical theory, when I want to come back to classical theory, so if I want to go from a theory in which I have this sea of photons, of discrete quanta of the electromagnetic field, if I wanted to go to the classical theory, in which I can write down continuous equations for my electromagnetic fields, the Maxwell equations, well, I lose all these properties. I lose the discreteness. I don't have the quanta anymore. I lose the fuzziness, and I don't have any more probabilistic description of my system. I rather have classical equations, deterministic equation. Okay, it's good to spend some time about these things, even if they should be digested, because then things, of course, get more confusing when we go to a quantum theory for another field, that is the gravitational field. Okay, so we were here, we were considering quantum fields living on a fixed background of my geometry, my space-time. Then, after Einstein, we know that after the discovery of general relativity, we know that space-time itself is a field. In fact, it's a covariant field. Covariant meaning that it's a field that whose physics doesn't depend on the coordinates that I want to use to describe it. So at this stage, I have quantum fields. I have one particular field that is the covariant field of gravity, of general relativity. And then, because on this side, I know that all the fields have quantum properties. I start from the assumption that in the world, in reality, everything is quantum. And what we see in the classical worlds is just an approximation of some deeper laws that are the one of quantum mechanics. So the gravitational field should be described, should have quantum properties and should be described as a quantum field as well, inheriting its property to be a covariant field. So I want a covariant quantum field theory. It should be a quantum field theory where I implement invariance under diffeomorphism. Okay, it's not. People are very confused about how to do this. Seems simple in words. Of course, people have been struggling to do this for many years. My work is in loop quantum gravity, where in these days we have a tentative framework in which what I described before is realized. So, and in the end, the final result is nothing so mysterious. In fact, what I needed to do in order to have to write down my quantum theory for the gravitational field is to have a Hilbert space, to have a good definition of a Hilbert space, to have a good definition of the relevant observables, the algebra of observables, and to have a good definition for the dynamics. So the three of them have a satisfactory definitions these days in quantum gravity. And so I can try to address the questions in this framework, the questions that I showed you at the beginning of this talk. So the situation is not so different than before. So remember, this is the picture I had before. Now, instead of a fixed background, as I say, Einstein discovered the fact that space-time is in itself a field. So now this field has a dynamics. It's not just a background, has its own dynamics, so it can bend. And what I want to do is to give a description in terms of its quantum properties. So instead of this smooth geometry that is represented by some pseudo-Riemann geometries in general relativity, then I will have quanta of space-time. And the theory describing them is given, so I have a Hilbert space, so my states live in this Hilbert space. Later I will describe better in which way they are characterized. I have a set of observables, again I will discuss later, and finally I have transitional methods. Careful here, so as before, the quantum theory is characterized by some discreteness. And this discreteness, as I said before, comes from the kinematical part. The fact that I have operators, that in this case are operators representing my geometry. So this means that I can have operators describing the area, the volume, the angles. So I write down those operators, I act on those states, and I discover that those operators have a discrete spectrum. So the discreteness in the theory is a discreteness, as before, coming from the operators. One should be careful because sometimes the discreteness appearing in quantum gravity can be a bit confusing. I wanted to stress this a little bit because, in a sense, quantum gravity is a theory of space-time in which, because of the quantization, we introduce this new discreteness. Instead of a continuous space, we want to describe a discrete space. And we know from the early days of quantum gravity that there exists a minimal length. And this minimal length appears naturally, directly, when you try to combine quantum mechanics with the general relativity. In fact, so if you take the Heisenberg uncertainty relations, you know that if you want to localize something with an arbitrary precision, at a certain point you cannot. So, in order to get a better precision, you need to go to higher energy. And because of general relativity, we know that if you try to concentrate more and more energy in a finite region, then you form a black hole. So this means that, so the more you try to localize the thing precisely, the more you need to concentrate energy in a small region to the point in which you form a black hole. But once you have a black hole, you don't have access to the region anymore. So this means that there is a minimal region beyond which there is no sense to talk about localization. And this minimal length has been first written down by Bronstein, and this is just combining the fundamental constants h bar, g, and c, you get the Planck length. So in quantum gravity, this Planck length play a fundamental role, of course, play the same role in a sense than, I don't know, when you do special relativity, you can see special relativity as the discovery that there is a maximum speed of light. You can see quantum gravity as the discovery that there is this minimal size. But again, when you want to implement this information in your theory, you don't have just to plug it in a rough way. You should know that this Planck length, this quantity, will appear in the discrete spectrum, in the possible values of your observables in the quantum theory. Okay, so we can draw an analogy with what was happening before for the electromagnetic field. Now we have this. My spacetime is a discrete spacetime made of quanta of spacetime. Carefully here, I say it again. They are quanta of spacetime. These are the fundamental objects, not just quanta of space, quanta of spacetime. Spacetime itself is discrete. It's a four-dimensional object, Lorentzian four-dimensional object. There is a fuzziness because when I study my algebra of observable, and again I have the fact that the operators do not commute, and again when I want to write the dynamics, this dynamics will be written in terms of transition amplitude. So what I want to write down are probabilities. So I can have a certain state describing a certain state of space-time. So I can describe a given geometry. I can describe also another geometry, and the question I ask myself is, what is the probability if I have a given geometry to get the other one? I wanted to take the classical limit. Classical limit means that I have a quantum theory of space-time. I wanted to recover the classical smooth space-time described by the equations of general relativity, where then I have, again, this pseudo-Riemannian manifold. How do I do it? Same as before. I just take the limit of h bar that goes to 0, and in this limit, the discreteness disappears. I had quanta here, the discreteness of this quanta. So it's like as if I was going to a different regime in which I don't see anymore the granularity of space-time. I cannot perceive the quanta anymore. The fuzziness disappears. Of course, I don't have anymore my quantum operator. And from a probabilistic theory, again, we get a deterministic classical equation of a field, where this field is the gravitational field that appears in general relativity, a field that in general relativity is described by the metric. So the metric, gravitational fields are the object I want to describe. Okay, now we are ready to try to address some questions. So the first comment I wanted to make at this point is to stress again, I take the classical limit. Classical limit, I learned it from my class of quantum mechanics, means h bar that goes to 0. I have learned also another limit from my classes in statistical mechanics and thermodynamics. This is another class, it's another subject. And when I wanted to study how a theory, a classical theory, emerges from a quantum theory, I don't talk about that limit. Okay. In loop quantum gravity, we have concrete calculations with which we can take this limit, recovering the equations of general relativity. The emergence of space-time is a standard classical emergence. So what I'm trying to argue is the fact that if I consider a quantum field theory, where, for instance, again, quantum electrodynamics, I have a theory that describes the dynamics of photons, and there is a sense in which from these photons, classically, these photons corresponds to the field described by the Maxwell equations. In the same sense, there is a theory, a quantum theory of the gravitational fields made of quanta of space-time, in which I can take a limit, getting back the classical equation of the general relativity. At the fundamental level, space-time is made of quanta, and of course, then I think that the real problem is not simply a problem in is not there is a problem arising here about the nature of this quanta, but it's not different. But it's strongly related to understand another theory that we have studied much better, that is simply quantum mechanics. So in quantum mechanics, when we ask what is real in quantum mechanics, I would argue that the fundamental objects that we describe are always quantum processes, rather than particles, rather than other objects. So, and of course we can debate this perspective, but I think that when you go to quantum gravity, this is a framework in which thinking in this way, I will have some slides later about this, thinking in this way is very useful because it provides a minimal framework in which quantum mechanics makes sense, general relativity makes sense, and the two of them combined still makes sense. I will talk more about this later. And of course, there is I was saying the space-time is made of quanta. This means that time is quantized as well. It's not the standard time. And again, I think that there is something to stress here that is not something specific of quantum gravity. It's something specific of general relativity. It's the fact that already when you consider general relativity, you don't have a unique time anymore. There is rather a multi-finger time. And in this sense, time disappears. Time as a unique object with respect to which I can describe all possible processes, all possible dynamics, doesn't exist anymore. What still exists are a multiplicity of times. In fact, I can choose any degrees of freedom as my time in order to keep on describing the dynamics. Describe the dynamics means to describe how things change, but this change is not with respect to an absolute line, a unique time for everybody, but it's a change always with respect to something else. It's a relational time. There are many infinite possible relational times. Okay. So I wanted to take some time to describe a bit more in detail the objects I introduced before, the Hilbert space, the states, the observables, and the dynamics of loop quantum gravity in order to make things a bit more concrete and to give you to show you that there is a concrete realization of these ideas that is available today. So the starting picture is the one in which I want. What is a state in quantum gravity is a collection of quanta, and before I had when I was considering electrodynamics, I had quanta there, and I was giving a position. I was describing this quanta by giving a position with respect to spacetime, to my background. So here I don't have a background anymore, and the only things that make sense is to describe the localization of this quanta as adjacency relation, saying which quanta is in interaction with the others. So I use a graph to say who is next to whom, and so this provides a localization, but localizing is equal to interacting. There is no difference between these two things. Again, it's the same as in general relativity. If I wanted to know where is something, I cannot give an absolute localization. I always need, for instance, to give the coincidence of two geodetics. So it's always a relational localization. Here is the same. The only meaningful thing that I can do is to say who is attached to whom, and saying who is attached to whom means who is in interaction to whom. So these lines are providing me an adjacency relation, but then I can add an information on each of these lines. I can add a quantum number, and this quantum number tells me how much each quanta is interacting with the others. Okay, and I discover later that this interaction is exactly what gives me the notion of area. Okay, so this is the object. Each of these objects is a Lorentzian quanta or space-time, but in fact this is a technical point that I want to add here. So in the formalism that we use, all the quantities are defined locally. We never try to define things globally, like giving boundary conditions and infinity. So what we want to do here is to consider a finite region of space-time, a finite four-dimensional region, and characterize this. And once I choose this region, there is a boundary of this region that is a three-dimensional boundary. So choosing this boundary implies also to choose a normal, and I can gauge fix my system such that this boundary corresponds to a space-like region. So this implies that instead of using the Lorentz group, I can actually use just a subgroup of the Lorentz group, that is the group of rotations. Okay, this is just a technical thing, and that I needed because, so what we do, in order to construct a theory, loop quantum gravity, you need to introduce a fundamental symmetry, that is the Lorentz symmetry, plus a dynamical equation that I will describe later. So this fundamental symmetry is the Lorentz one, and therefore the variables that I use are group variables, but instead of the Lorentz variables, you will see here SU2 variables, so variables valued in the rotation group because of what I said before. Okay, so I have my states that are characterized by a graph, by some quantum number living on this graph, and by these group variables. I discover that having these variables that satisfy, so these variables that are SU2 variables, having them satisfying this constraint, so this should sum up to 0. We know after Penrose that it's equivalent to give a notion of geometry. So once you have this, you have a notion of geometry. And yeah, so this is the kinematical description, the description of my kinematical space. And you see, from these variables, I have called L, those are the building blocks from which I can write down all the relevant observables in my theory. The observables describing a geometry. So, does it mean to describe a geometry? It means to have a way to measure area, volumes, angles, and so on. And as I said before, these are operators with a discrete spectrum. They are fuzzy because they do not compute, and so those they really characterize a quantum geometry in the sense that I can have the most general state would be a state in which I have superpositions of possible geometries with different values for these quantities. Okay. The dynamics. So I have those states. So the starting point is this four-dimensional Lorentzian region. I consider the boundary of this region, and I write down the states living on this boundary. And then I wanted to ask what is the probability. So suppose, well, let's split the boundary in two parts. So I may ask what is the probability to go from this state to the other state. Or, well, if you look at this, it will be just, if you think at one state, I can ask what is the probability of this state to be realized? What are all the possible four-dimensional geometries, Lorentzian geometries, that are compatible with this three-dimensional state? So, and what is nice is that, so you can think about this probability amplitude as a history of the geometry to go from here to here. You can interpolate this region with graphs. It turns out, in fact, that they can be interpreted as Fanon graphs. So they are really the graphs giving you the dynamics. And so I can have a history of those states building up a graph, what we call a spin form, inside this region. And we have, once you have this kind of graph, we have Feynman rules associated to this. So after those Feynman rules, we can write down an expression that gives us a probability, again, to go from one state to the other. So this is the definition of the dynamics. Let me stress again that is a Lorentzian dynamics that is local in the sense that there is an expansion in terms of a vertex. The vertex are those embodying the dynamics in quantum theory. Right? So here we have exactly those kind of objects. And finally, in the recent years, from 2009, we had mathematical theorems showing that this object gives you back the Einstein-Hilbert action. So namely the action, the dynamics of general relativity. Okay. So, okay, of course, this is a bit, I hope I have not scared the philosophers. They are not too much into these things. I wanted to go to the main that is the fact that, so we want to describe a region of space-time, and this region, so now a region of space-time is at the same time a region of space-time, but it's also a quantum process. So imagine I have this boundary. I can make a measurement, a quantum measurement, really in the sense of quantum mechanics. Suppose I make a quantum measurement here. I make a quantum measurement here, and everything that is in the between is what I call a quantum process. And this quantum process is nothing but what we call space-time. I cannot convince you unless I try to explain better what I mean by quantum process. And this is related to a particular point of view in quantum mechanics. So what I would like to stress is the fact that in almost all interpretation of quantum mechanics, you always need two systems. You always need to make a split in the system you are considering between the observer and the system observer. This is true in the Copenhagen interpretation, it's true in the many-world interpretation, and is particularly true in the so-called relational interpretations of quantum mechanics, where all the values of the variables are always relational. So states are all quantum states. All the quantum states are relative states, and what is interesting here is the fact that what is interesting for me in this interpretation is the fact that the fact of highlighting the relationality in quantum mechanics makes it compatible with general relativity, with the relationality of general relativity, and therefore provides a meaningful setting for doing quantum gravity. I don't. Okay. Am I doing with time? Yeah. Okay. I wanted to come to the end of the talk, but we are almost there. So. So the fact of taking this interpretation of quantum mechanics, in which we highlight the role of processes, allows me, by basing the construction of my theory on the notion of locality. So the fact that I describe my locality enters in many ways in the construction of the quantum gravity theory, as I said, because of this notion of adjacency when I write down the states, and because of the vertex expansion that I use to describe the dynamics. So the definition of processes, again, I said it again. A process is what happened between a quantum measurement and another quantum measurement. This notion of process can be put in correspondence with the space-time region, and the boundaries of my space-time region are the states of my quantum theory. This is so. To conclude, what I wanted to stress is that a relational perspective in quantum mechanics, together with the fact that there is a relationality in general relativity as well. As I remembered before, whenever you wanted to express localization. This localization should be also should be always given in a relational way. For instance, as I said, by considering a crossing of two geodetics, or another way in which the relation. So this is one of the way in which the relationality appears, and the root of this relationality is the fact that time is just a gauge in general relativity. So, and gauge variables are variables that we cannot predict. We can measure them, but we cannot predict them. So, and only when we combine two gauge variables, like time with another gauge variable, then we can have a gauge invariant quantities. That is something that we can predict. This is true in general relativity, and inherits in the quantum theory of gravity. So you see the relationality here and the relationality here converge into this theory, the theory I have described before, in which that is a theory of space-time, but again, space and time change their meaning. So I can go back to my first slide, that was this one. So what is space? What is space in quantum gravity? Is this? It's a process. Well, a space-time region is a process. The states that are the boundary of this space-time region are made of quanta of space. So what is space? Space now is made of quanta, and so we can argue whether. So I go directly to this question. So, do we have a space-time in this quantum relativistic regime? Well, it depends on what you want. You decide now, at the light of a quantum theory of gravity, depends on what you decide to call space-time. So if you decide to call space-time that object that is a Riemannian smooth geometry, a Riemannian smooth pseudo-Riemannian smooth manifold, then of course we don't have it anymore. We have something else. We have a quanta of space-time, and it's up to us to decide what we call space-time and what is not. Again, what is time here? Is there a time or not? Depends again on what you decide to call time. If by time you mean the classical notion of a single variable with respect to which you can describe all the possible dynamics, of course this doesn't exist anymore. In fact, it disappeared already in general relativity. There is something else. There is still a notion of change, and this change is a relational change in which I can evolve one system with respect to another. I can evolve a quantum system with respect to another quantum system, one respect to the other. So, and I can make a history of this change. So I can store the information about a sequence of change in my states. So does it mean can we call this time? Well, it depends. You have to qualify what you decide to call time. So what does emergence mean? Well, here I tried to make as clear as possible the analogy between what we do in quantum gravity and what we do in the quantum theory of electromagnetism. So I argue that what we have to do with the quantum theory of gravity is just to repeat what we have learned from electromagnetism. Eventually, maybe we have not learned enough, because I don't know how much it has been investigated, how the Maxwell equations emerge from photons. Of course, if you look at the mathematics, there are always mathematical details that do not fit. But I think that from the perspective of a physicist, it's clear that we have photons, and from them you have the Maxwell equations. And from the perspective of somebody working in quantum gravity, the picture I have in mind is that I have a quanta of space-time, and from them there is a sense in which gravity, classical gravity, emerges. Do we need a thermodynamical limit to do this? Well, my answer is no. What does it mean to take a thermodynamical limit? It means that you have to take the limit for an infinite number of quanta, or very large number of quanta. So, in the equations that I have shown you before, I have defined the states. So those states can accommodate an arbitrary number of quanta, little elements of volume and area, and so on. And and I have shown you the dynamics of the theory. So if I consider the case of the analogous case of a Fock space, I can define a state in the Fock space in which I have only few photons, maybe even one photon, and I know the transition amplitudes, I know the Feynman diagrams. For instance, I know a Feynman diagrams for some photons going into another number of photons, and this is all I have. And this already codes electromagnetism. I don't need to go to the limit in which I have an infinite number of quanta in order to know that my theory is describing electromagnetism. In quantum gravity, I have my states. So these states are can be coding one quanta of space-time to quanta, many quantas of space-time. I have my dynamics, and so in the states I am coding. So I have the information that the fundamental symmetry is the Lorentz symmetry. I have the information that my dynamics is that one, the spin-fold one, and this is just the quantization of the Newton's law. So these two things together are enough to give the equations of Einstein equations. Are enough. So these two informations, it's a calculation that you can check, you can do. These two informations together are already enough to give you the Einstein equations in the same way in which if I take the Gauss law and implement Lorentz invariance, I get the Maxwell equation. So I wanted to conclude by saying that we have a tentative theory of quantum gravity in which we can try to answer to these questions. And the very last questions, the very last two questions, what is emergence and what is the thermodynamical limit? Well, we have to not to look for any mysterious thing, but just to take seriously what we know from what we have learned from quantum field theory. Eventually, maybe we should learn more about quantum field theory and how classical theory emerges there, from the quantum theory to the classical one. But this is not what we need to do in quantum gravity to recover classical space-time. Thermodynamics is a very interesting and fruitful subject that is worthy to explore, but is not the one we need to get classical spacetime. It's a different problem. And I think I can conclude here.
Okay, so usually we start with questions from the other end. So, maybe in Chicago, do you have questions there?
Yeah, so I do. So in field theory, what people often say is that to get, the classical field, to get a classical field out, you have to look at the coherent states. Those are the ones where you end up with a sort of minimum uncertainty between the position and momentum of the field. But those are infinite particle states. Right? I mean, they're a superposition of every number of particles. So it's not the thermodynamic limit, but that would mean if you just have a finite number of particles, there's some largest n in your superposition of particle states, you don't have a coherent state. So I guess in particular the result you were talking about, does that assume that you have a coherent state, or is that supposed to happen even for sort of a single?
Okay, so
I'm just kind of confused about this issue in general, actually.
Well, one of the techniques indeed to get the classical limit in loop quantum gravity is to write down the coherent states. And these coherent states are written for a specific state where I consider indeed a superpositions of all the possible configurations of this state. So when I write down when I write down the coherent states, indeed, when I write down the coherent states, indeed, I am summing, I am integrating over all possible values, and those are the values. Those are all possible values. For instance, so if I consider a quantum gravity state, okay. So let me take a simpler case. I consider the case of a coherent state for a simple particle, and these coherent states will be picked on a given position and momentum. And then, of course, I have an integration over all possible positions and momentum. In quantum gravity, what you do is the same in the sense that I can write down a coherent state in which I pick the coherent states of a particular couple of conjugate variables. So what was the positions and the momentums for my particle became the area and the curvature, the sensitive curvature. So I can write a coherent state that knows about this a specific value of area and curvature, having all the possible having fluctuations around all the possible values for those quantities. So in the example that I gave, I am considering a single particle, and for the coherent states that I'm considering for general relativity, for loop quantum gravity, I'm considering the case of a system, a certain geometry that is just a geometry described by a finite number of degrees of freedom. So in order to write this coherent state, I don't need to take a limit in which I take an infinite number of degrees of freedom. It's true that I think that maybe a way to disentangle the problem is can you go to the last slide that I had in my compliments? And I had
the comments further back.
Yeah, later on the last. Yeah, exactly this slide. Can you see it, Nick? Mm-hmm. And can you see me?
Yes.
Okay, so I think that in order to answer to your question, maybe we should. It's good to discuss this graph in which. So what I was discussing before is this thing, is a theory in which I have a finite number of degrees of freedom, the quanta I was discussing before. I take the classical limit, h bar goes to 0, and I get a classical theory. There is another limit that is this one, C, that I call it C that goes to infinity, that is indeed what would correspond to the limit in which I take infinite quanta that we were discussing before. And what I call what is this limit is what we call the continuous limit. So I can get a classical theory that is a discretization of the classical theory, but the discreteness in this theory is not a quantum discreteness. It's just because it's the same kind of discreteness that there is when I put my theory on a lattice, or when I wanted to put my equations on a computer, so I have to discretize them. I can have a discrete, but I can put classical equations in my computer and solve them. And so it's a classical theory, discrete classical theory. The thing that I am discussing is this limit here. There is another limit that is the continuous one, which indeed I have to take an infinite number of quanta, of space-time quanta, and this will give me a continuous theory. I would argue that this limit don't exist, in fact. Don't exist in nature. It exists in our theories, but it doesn't exist in nature. This limit cannot exist. For a very simple reason that. So I wanted to describe some space-time region. At a certain point, this region should be given by a finite number of quanta of space-time. So of course you can define the continuous limit in a mathematical way, but well, again, it's an interesting limit that can be studied, but this is not the one in which we are interested. And if you wanted to check, if you wanted to see the relation between the quantum theory that you're doing and the classical theory, this has nothing to do with that limit there. I don't know.
Okay.
If you want, yeah.
Have a finger on that, unless Nick wants to come back.
No,
so,
go ahead.
Aren't there ways, though, in which you can more directly connect what's at the bottom left of that slide and the right top by looking at, for instance, the geometric operators that are defined in the quantum theory, in loop quantum gravity, and to connect them to quantities of space-time regions like areas and volumes in the classical continuum theory? And sort of show how they're supposed to be approximated, at least in sufficiently well-behaved states.
Well, I haven't seen it realized. I don't know whether it is possible or not. I haven't I haven't thought about this. So the problem is that the discretization procedure is something that I see, the discretization that is different. I use the word discretization to talk about the discretization of classical equations, for instance, as opposed to the quantization, okay? So the two words I want to use to address one thing and the other. So the discretization, I think that is something that we cannot really avoid in doing a quantum theory of gravity. And the reason is the following, so the discretizations come from the fact that I was it's the fact that because of the invariance under diffeomorphism, again, there is this idea that the only meaningful thing is that this notion of adjacency, this notion of interactions between different quanta making up my states. And so I think that I don't see any way in which you can. So you can take a limit. Of course, you can take a limit to an infinite number of relations, an infinite number of connections with an infinite number of quanta. But in principle, mathematically, of course, you can do it. But is this physically meaningful? When I work with a Fock space, I don't consider an infinite number of quanta. All the process that I'm interested in, they are always processes in which I consider a finite number of degrees of freedom. I consider a state with n, a finite n number of quanta, an n number of photons, finite, maybe just few of them. So I don't take in all practical situations I don't take this limit, and also that's the same. So this is true at the level of the states, and this is true also at the level of the dynamics, because when I consider the dynamics in terms of Feynman graphs, so there is this discretization of the states living on the boundary, but also I can discretize my region. I don't know, like I can split this region in a way in which something like this, in which I have some interaction vertex here, and I am discretizing it in different space-time regions. So this is what codes the dynamics. It's the analogous of my Feynman vertex, the interaction vertex in the Feynman diagrams. And so when I do quantum field theory, I take an expansion in vertex, and when I get to, I don't know, or maybe people are computing things to the order of times, no more than this. And so again, in principle, yes, people could be interested to consider the limit mathematically, but I don't think has meaning for practical computations. Then, of course, we are interested in. We are here in the philosophy department. We are interested in the true deep nature of these things, but again, then the picture I have in mind is that there is a fundamental discrete nature of these things, for which, yes, okay, you can take this limit, meaning that you take the limit in which you have many quanta, but that's true. I think that there are many quanta of space-time building up our universe. Yeah. So well, in order to conclude and qualify a bit what I'm trying, the message that I'm trying to convey is that there are two different discreteness in quantum gravity that should not be confused. The discreteness that we use to write down the states is a discreteness that we introduced because of our way to interact in the system. So choosing a state here corresponds to choosing how many degrees of freedom you want to describe. So in a certain sense, this is related to the way we interact with the system. So it's not deeply, so in a certain sense, it is not a very deep discreteness. What is really, I think, the core of the theory is the fact that there is a quantum discreteness, and this is the one about which I think I have no doubts.
Okay. Nelson?
Just a small point. What's the relationship between the coherent state approach to the semi-classical limit and the wave state approach?
Well, the coherent states are, in general, techniques that are used to get the semi-classical states, not in quantum gravity in general,
yeah.
right? So. When you take a coherent state, you take a superpositions of many states, and this state is such that is peaked on particular value. This is what was explained before. It's a particular value of your conjugate variables, positions and momentum. Here, the conjugate variables in general relativity turns out to be area and curvature. And yeah, the point is that you can write a coherent state for a single particle, or you can write a coherent state for a field in quantum field theory. And the same can be done here. When you take a coherent state, indeed you are integrating over positions over x in the case of in the case of coherent states in quantum field theory, in electrodynamics. But this means that so you're integrating over all the possible case, for instance, all the possible momentum. In our case, it could be so you can have superpositions in which you integrate over our variable that is actually yes. So you integrate over SU2, for instance, that is our group variable. I don't see, so the fact that you are integrating over all possible k, so if you go to the coherent states, this is the expression I was writing before. So when you have a coherent states in which you have an integration in k of so this is giving you probably almost probably I'm getting some so you see, so this is the creation and annihilation operators for instance, you can create and annihilate photons. You have an integration over k, over the momentum, but in the end, so and analogously in quantum gravity, you can have an integration over your u variable that is a SU2 variable. But yeah. Okay, so this gives you connects you with the classical equations, because in the case of the particles, you can have this gives you a wave packet that moves following classical trajectories. And that's the same that happens in quantum gravity. You can write down equilibrium states, pick down some geometry, and the dynamics of the geometry follows the classical trajectories. So the classical dynamics given by general relativity.
Yes.
But I don't see where is the thermodynamical limit related to.
Yeah. This is some years ago there was this literature on the wave states in quantum gravity.
Weave states.
Oh, weave, sorry. Weave states.
Which?
Weave states.
Weave states, the particle states, eigen states of the area operator, for instance, having eigenvalues, classical eigenvalues.
Well, close. That's what I meant when I was referring to your slide.
Approximately classical values.
No, but the thing is that you can write down queer states, and so the best way to write the queer state is when you have it equally spread in position and momentum, and so a good queer state, the one I like to work with, they are equally spread in area and curvature. Of course, instead, what you can do is to write down queer states that were picked all completely sharply picked in the area or completely sharply picked in the curvature. In fact, this was easier to do. This was done before, earlier than the equally spread queer states. And you can do that. But you can do that. It could be useful in certain situations. Yeah. So, but what does it mean? This it means again that you pick your geometry on a certain value, classical value, plus you have the fluctuations given by the fact that you are summing over all possible geometries, underlying geometries. So. Yeah, so maybe the fact that, but this is related somehow to the fuzziness that I was discussing before. The fact that when you go to the quantum theory, it's quantum theory of space-time, and in general, the most general state is a state that is a superposition of many geometries, and eventually see a geometry with even though maybe usually when you wanted to describe a certain, so when we compute the kind of calculations you want to do are such that you fix a certain geometry, you fix a final geometry, and you want to know the probability to go from one to the other. So you wanted to write down some states for a certain geometry that you know. You can measure it. You go there with a test particle, you measure a certain geometry, and then you wanted to know the evolution of this state. Okay, so when you write down this geometry, usually what you do is, so you write down a state like this one, and so this state has a certain number of degrees of freedom. This is what I was saying before. So this is related to the way we interact, the degrees of freedom that we want to describe. Suppose I wanted to describe a system that is such that a certain number of degrees of freedom, so I have each of these is a node, a link, etc. So for each of these dots, I have 1 degree of freedom. For each of this link, I have another one. So I don't know how, I don't want to count them now. Okay. So you start from this, and you write down a coherent state that has those number of degrees of freedom. You have all the fluctuations, of course, of the geometry, fluctuations of the possible values. So on this link, I said I have these two little volumes of space-time that are interacting, and there is an area, and this area is coded by quantum number. So it's fluctuating, and this means that, so if my state knows about different values of the area here, of the interaction here. But then, and I can decide to pick my state in a way such that I fix the area here and I let the other fluctuate, for instance. Or I fix all the areas, but I let all the curvature to be completely fuzzy. So the relevant point is that there are those fluctuations. That means that the area, the volumes can take different values. I have superpositions of those quantum numbers. But when I choose the degrees of freedom with which I interact, I'm not interested to choose to change those numbers. Then there is something else. Of course, then with the dynamics. So this is the kinematics. This is the way in which I write the states. Then the kinematics may be such that I create a new degrees of freedom. That's another story.
Okay, we have a few more questions.
Well, I just have from a non-expert, let's say, how do you put up this with the gravity?
Oh.
So if the graviton really is an excitation of space-time and space-time disappears,
well, the graviton is what we call graviton is a special case because it's in the semi-classical. Is this theory, but in its semi-classical limit. So, in order to have a graviton, so what we call a graviton is a small excitation over a given geometry. So this means that you may have Minkowski space. So you can have a Minkowski space. You can have also a curved, I don't know, like a Sitter geometry. And then on this, there a small excitation, and this framework allows to compute the graviton propagation. Even though I want to stress that this provides a full quantum dynamics, and if you want to describe the graviton, you are already going into a semi-classical limit, and in which you do perturbation theory, and then what you want to do is to recover the results of people doing perturbation theory in which there are results of gravitons. So when that's why I'm talking about quantum space-time. I have never used the word gravitons because the word gravitons is associated exactly to this specific thing, that you have some geometry that is almost fixed, which you have some very small perturbation. This framework allows to describe the geometry allows to describe the classical geometry, but it allows also to describe the wildest quantum geometry you can imagine. Then you discover that those very wild geometry are in fact suppressed. That's why we don't see them. It's very difficult to see them. So the dynamics itself show you that you don't see this wild geometry, but they exist and they are there in theory.
Okay.
So this is somewhat going back to the earlier discussion in a different way. So, I mean, what I heard from the early part of the talk was that the key, what was key to the classical limit, or key to getting sort of classical fields back out, or sufficient, I guess, it looked like was just taking the h bar goes to 0 limit. But I have a hard time sort of understanding that. I mean, in the electromagnetic field case, I can kind of understand how, one photon or two photons or 10 photons might correspond to some really kind of weak classical electromagnetic field. But I'm really having a hard time now thinking about what you mentioned, the paper on the classical limit, the Barrett and a whole load of other people paper. Does that result actually require, I mean, a special state, like a coherent state, to actually go through? Otherwise, if it just requires, if it holds, even if there's like 2 or 3 nodes or something, I just don't understand how one could be getting some GR out of that. There just doesn't seem to be enough stuff there to be getting a spacetime. So does it actually also involve not just h bar going to 0, but also a restriction to sort of special states, presumably the coherent states?
That's a very, very, very complicated question. So I think if a person, I think it's one of the hottest problems in quantum gravity to really manage that limit. And beside the work of Barrett and the others, I want also to cite the work by Mushinan more recently, and other people. Well, Mushinan, I think it's the person who worked most on this more recently. So, and the result is indeed very complicated, and I don't dare to go into the details of the computation. It's true that taking the classical limit in those computations were done by considering queer states and considering a saddle point approximation. And furthermore, if you look at the work of Mushinan and also the earlier work by Magliaro and Perini, well, what you have to do is not really to take h bar that goes to 0. There is a more complicated limit in which you want to take a limit in which you keep on having you have to manage to have well. That's the way in which we actually take the classical limit in quantum mechanics. You know that if you have a theory with Dirac brackets, with commutators, you can take a limit in which you take a very high quantum number, and the theory goes into a classical one where the Dirac brackets are replaced by the Poisson brackets. So that's why here what we do, we use the same techniques from representation theory. So the actual limit that we take is the one in which we take the quantum numbers being very high, and then again there are subtleties in the way in which you do it, because you want to tune it to take this limit while keeping the minimal area fixed. So this is rather technical, and but I think this is not the interesting part of what I want on which I want to focus. Because, so I'm sorry, this would be a talk. This is something that I prepared for tomorrow, but I think I can anticipate it now. The thing is that there is already, so yeah, besides the technicalities that you use to take this classical limit that involves some involving mathematics, there is something that you can already observe when you study the theory. This is what I was saying before. It's the fact that consider what happens in electromagnetism. So originally the Maxwell equations were written in a horrendous way, pages of equations without any order, any beauty. And then, well, now we study them in a much compact way. And in fact, there is my favorite way to write them that amounts just to take the Gauss law plus the Lorentz invariance, combining the two of them, and the unique solution that you obtain are the Maxwell equations. In the same way, for general relativity, you can start by considering the Newton's law. You have to add general covariance and Lorentz invariance, and you discover the only equations that satisfy those requirements are the Einstein equation. So, Newton's law, Lorentz invariance, invariance under diffeomorphism, those are all classical concepts. And this construction is a classical construction that gives you general relativity, a classical theory of gravity. Now, there is a way in which, the way in which the theory on quantum gravity is constructed implements all those things in the sense that there is fundamental symmetry, that is the Lorentz invariance. I have my group variables comes from this Lorentz invariance, and I have the Newton's law. The Newton's law. This is going to be what I will discuss. Well, I will show you tomorrow that this expression was there. The expression giving you this interaction vertex is exactly an expression, a classical expression that embodies the Newton's law, in which you promote your physical quantities to be operators. So, and then, okay, you remove the hat of your operators, so you are back with Newton's law, Lorentz invariance, general relativity. So this is. So we can go back and forward. Go to we have constructed all this theory coming from a pure quantum theory, and all these people have tried very hard, worked for years in order to show us that this theory was giving us general relativity, classical general relativity, with those complicated calculations that I cannot reproduce here right now. But in the end, everything was already written here. What we have discovered is that we were just promoting to operators a classical relation that is the one that embodies the Newton's law for gravity. So I cannot think of a simpler way to see the relations between the quantum and the classical theory as it is realized here.
Okay, are there any more questions or comments which are both short and urgent?
I think I have a short question. I don't know if the answer is short.
Okay.
Shall I ask it?
Go ahead.
Oh, okay, we lost sound for a minute. Can I think of the nodes as space-time points?
So first of all, it's a very good question, thank you, Nick. And this is actually easy to answer, easier than the one before, in which you were asking me to reproduce those horrible calculations. So this is an easy one. I I have always been talking about space-time quanta, but in fact, I was also showing you that in order to write down the states and compute those transition amplitudes, then the states are in fact three-dimensional states. And yes, I can consider each node as a space-time quanta, but in fact, for practical reason, we always choose a gauge in which the quanta is actually a space quanta. This is so you did this in a time gauge. So in general, so each node in the states, because the states lives on the boundary, it's a three-dimensional object, and in principle it knows about Lorentz invariance. It could be mixed. It doesn't have to be a space-like thing. It could be mixed space and time thing. For practical reason, all the time that you write down the state, there are people who are trying to implement fully Lorentzian states. In the concrete calculations that we do all the time you look at the states in textbook and articles and so on, then we are always using this time gauge in which in fact these three-dimensional quanta are quanta of space and not quanta of space-time. So each node indeed is a three-dimensional quanta of space. It's a little volume, a little ball, fuzzy ball or volume. But then your question was, can I think about it as a point? No, I cannot think of it as a point. And in the sense that the region occupied by this quanta doesn't have any notion of localization. There is no localization inside the quanta. So the quanta, each of these objects is an elementary piece of space-time. And there is no space-time, there is nothing that exists outside the quanta. So the quanta makes up space-time themselves. And each of them is an elementary thing, and every time that I wanted to think about localization, it's a localization between at least two quanta. So what is meaningful, again, if I have two quanta, the two balls, I don't know if you can see this. So I have my little fuzzy piece of space-time here, and I put a dot here. That's the node of my graph, but it's just to remember it. Let's forget about this. And I have another quantum here that are interacting. Dot here, and then I link them. This is to say that this link represents the interaction between the two, and the link is put for our convenience to talk about the interaction. Is not something that exists in the same sense in which this point, this node, does not exist. It exists the full little quanta of space-time, and then everything that I can describe is this interaction. That I like to think of them as the cross-section, in fact, of an interaction. So when we describe interactions in quantum field theory, we talk in terms of a cross-section, that is an area. And oh, look, here in quantum gravity, the very notion of area is exactly this. Is this in how much these two quanta are interacting. So, so there is no point, this point doesn't exist, this point doesn't exist. Everything that exists is just this region and the area that I associated to this interaction. So in particular, there is also, I would like to stress, there is no point and there is no distance between this and this. So it exists an area, it is this interaction, and it exists a volume, three-dimensional volume. Or eventually I can also, and then when I write a spin form, I am considering I can give you the four-dimensional volume of this four-dimensional Lorentzian objects. But yeah, okay, that's
that's all quantum mechanics. That's all at the quantum level, right? It's not.
Can you repeat, please?
Everything you just said is in the quantum regime. You're not thinking in a classical limit at all here.
So in the classical, in the quantum regime, there are no points.
Yeah.
There are
everything
quanta, but they are not infinitesimal points.
Right. But there are those those regions and areas you were talking about. They're quantum.
Yes.
Okay.
Yes.
Right.
So the other thing is that this area is quantized and it comes with it's proportional to the Planck length, and it comes on multiples of the Planck length. So,
but I can think of them as kind of pieces of space-time, so to speak. Because I think that's
in the same sense in which a photon is a piece of the electromagnetic field, yes, definitely yes.
Okay, that brings us to the end. Please join me in thanking our speakers.
Thank you very much. That was great. Really enjoyed that.
Thank you for your questions.
Okay. All right. Enjoy your stay. Bye, everybody.